Hi everyone, we are Group 18 and we will be presenting on our project on hand graph classification with graphs. We will first introduce the project and our objectives, then the dataset we use as well as pre-processing of data. Then we will describe the models we use and the results obtained from these models, and finally we will conclude the presentation. Starting off with the introduction, in recent years, hand gestures have emerged as a novel and natural way of interacting with computers. Algorithms to recognize hand gestures from image data have made such interaction possible. One of the many use cases of such algorithms is in the recognition of sign language gestures. While the types of hand gesture recognition tasks are numerous, in our project, we aim to develop a model that can classify static images of hand gestures into classes that are either within the training dataset, a task that we shall call the in-distribution or ID task, or outside the training dataset after being supplied with a few examples to compare to, a task that we shall call the out-of-distribution or OOD task. This diagram shows how an OOD sample can be compared with a reference example to obtain a similarity score.
I'll now be going over the dataset that we've used for our project, which is the Hairgrid V2 dataset, which consists of 33 hand sign classes and over 1 million training samples. And as you can see on the image on the right, each image actually consists of 21 landmarks as well. And in the Hairgrid V2 dataset, it only has 2D landmarks on the x and y coordinates, and without the z-axis, we have no depth information. So to circumvent this, we actually used the media part library, hosted the model locally to perform hand landmark detection locally. So this gave us the x, y, and z coordinates of all 1 million images. And for our project, we also only focused on single hand gestures, so that means that classes like this that require two hands to form the hand signs will not be included in our project. Also, because the model should recognize gestures regardless of whether they come from the left or right hand, we merged these classes together as well. We also perform normalization pre-processing steps to remove variations caused by rotation, scale, and translation. So to handle random orientation changes, we aligned each hand to a canonical direction. This reduces viewpoint sensitivity and ensures consistency across samples. So this figure over here shows how two slightly rotated versions of the same gesture are aligned to a common frame, and after normalization, they map to nearly identical landmark structures. To make the model invariant to different hand sizes and positions within the frame, we scale each sample to a standard size, a 1 by 1 by 1 unit cube, and recenter it.
Next, I'll walk through the baseline model we use as a reference point before evaluating our graph-based approaches. Our baseline is a simple MLP that takes a canonicalized 21 times 3 hand key points, flatten them into a 63-dimensional vector, and classify gestures without using any relational or geometric structure. The goal isn't about high accuracy, but is to provide a lower bound reference that shows how much performance comes purely from raw coordinates before adding graph-based modeling. Baseline is a simple two-layer MLP with 18,197 parameters. It maps the 63-dimensional key points vector into 33 gesture classes. Since it contains no relational modeling or structural understanding of the hand, it serves as our lower bound benchmark. This baseline is important for 3 reasons. 1. It isolates structures prior. It shows how much performance comes purely from coordinate geometry before adding edges or relational reasoning. 2. It measures coordinate separability. If the MLP struggles, which we will see later, it indicates that the gestures cannot be distinguished from raw coordinates alone. And thirdly, it provides a fair benchmark. Any improvement from our graph-based models can be attributed to meaningful modeling choices rather than random chance. On the in-distribution test set, the baseline achieved only 15.03% accuracy, showing that it cannot distinguish fine-grained gestures from raw coordinates. However, it has a higher out-of-distribution accuracy of 54.94% and 73.77% with more support samples. And this comes from coarse global separability, which is not a true geometric understanding. So thus, this confirms that we need structures-aware models like GNN.
While MLP models capture implicit structure, they often treat the hand skeleton as a collection of features rather than a coherent geometric object. To complement these approaches, we introduce a handcrafted graph matching method that explicitly leverages the spatial relationships between joints. The graph matching procedure we have gone with includes 3 main steps. First, extract a descriptor from the hand pose. Second, compare the descriptor to a stored gesture template. Finally, pick the gesture class with the highest similarity to one of the classes in the gesture template. For OOD, we tested the performance of one-shot and few-shot prompting. For the matching metric, we decide on cosine similarity as it measures the directional alignment between feature vectors. So for the first descriptor we tried, which was the pairwise distance between all joints and angles between all joints. This was to help capture the relative spatial arrangement of all joints. The second descriptor we used was the unnormalized graph depletion to capture the structure and connectivity properties of the network. We also referenced the XR hand features designed for AR and VR applications and implemented for our own usage. This namely added the finger curl, pinch distance, and spread to the original pairwise distance and bone angles. And these are the results as shown here. So with pairwise distance and bone angles, they actually achieve a rather decent performance. The patient didn't do as well because it only captures graph structure, which doesn't change much between different gestures. And XR hands also didn't show a substantial improvement, as most of the features are already captured by the pairwise distance and bone angles. So to help understand what the matching algorithm is seeing, we built several visualizations. Some notable examples are for call, the index, middle, and ring finger having small pairwise distance between the different joints. And for the stop gesture, the bone angles are mostly 0, and pinch is 1 since all fingers are mostly straight.
The graph convolutional networks, that is our first attempt at using the graph structure with deep learning. So the GCN architecture is on the right. So you have a GCN layer where the nodes interact with each other, followed by a rectified linear activation function, and after which we have a residue connection that adds to prevent the vanishing gradients problem. You have 9 layers of GCN, as that's the maximum distance between two nodes in our hand graph, after which you have to aggregate the different node embeddings into graph embeddings, and then you have a linear layer to convert the graph embeddings into our desired number of dimensions. Now there are different aggregation techniques that you could use. One would be to mean all the node embeddings, and one would be to flatten them. Now flatten of course has a lot more parameters, majority of which being in the linear layer, and as you can see from the results, flatten tends to perform a lot better. The next comparison we have is again 2 different training methods, one being the Siamese and one being triplet. Siamese tends to perform worse on the in distribution data, while triplet tends to perform worse on the out distribution data. Now let's compare across embedding dimensions. We tried 2 embedding dimensions, 32 and 64, and the performance is roughly the same, even though 64 has a lot more parameters than 32. Next, we look at the Chebnet architecture. So the Chebnet architecture, we don't need to have layers since we're just using a higher order of the Chebyshev polynomial. So here, for a fair comparison, with 9 layers of GCN, we use the 9 orders of Chebyshev polynomial. So k equals 9, and the performance can be seen where GCN performs better on the in distribution test and slightly better on the out distribution test, and the number of parameters is similar, being slightly higher on Chebnet's side. The last experiment in the GCN family was with the GAT, or the graph attention network. So we tried different experiments with GAT, and you can see the results on the left, where GCN tends to perform at par or slightly better than GAT, even though GAT is more sophisticated and anisotropic by nature and also has more parameters. For GAT, the architecture is on the right side, where we have a multi-headed GAT, and we first mean the embeddings across the heads before adding the rectified linear and then the residue connection, and that is the same as the GCN architecture.
The next model that we have explored is the graph transformer. So why do graph transformers work well in our case? So firstly, the graph transformer performs attention-based message passing, and instead of using fixed neighbor weights, they dynamically learn how much influence each neighbor should have on each node and edge feature. Also, they are more expressive than GCNs, which apply the same convolutional kernel everywhere. GTs adapt their interactions instead to the local context and naturally respect the inductive bias of handmark topology. Lastly, the hand graph is small, and the longest path between any 2 nodes is only 9 hops. So we've trained 2 graph transformer models. The first one is a graph transformer without edges, which consists of the normalized landmark coordinates, and the second feature being the Laplacian positional encoding. For the graph transformer with edges, it consists of these 2 features as well as the third feature, which represents the edge direction. And this is the formulation that we've used to calculate that. And for the loss function, we use a combination of the semi-hard triplet loss and the cross entropy as well. The semi-hard triplet loss selects usefully difficult negatives instead of useless or impossibly difficult ones to stabilize gradients. And the cross entropy further stabilizes training and encourages faster convergence. And in terms of the architectural changes that we have made to our model, we've refined from the provided graph transformer code provided in this tutorial. The changes include the output layer no longer simply outputs the logics for classification, but also outputs the embeddings themselves. We have also added layer norm and gradient clipping to our model to stabilize training. Finally, here are the results for both our graph transformer variants. As you can see, the variant with edge direction features did not improve the accuracy. This is because these features are just linear transformations of the node coordinates the model already sees, making them redundant.
Finally, we shall conclude this presentation. As seen in the table above, the graph transformer achieved the best performance across the different tasks. Of particular interest is graph matching, which achieved comparable performance to the graph transformer in a few short OOD tasks. This indicates that it can be a good candidate for a low-cost alternative if sufficient reference data for comparison is available. Finally, for future work, KNN graphs can be explored to see if it improves the model performance. Problem regimes beyond the static case, such as dynamic gestures or two-handed gestures, can be explored. This brings us to the end of our presentation.